10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
You've probably heard the phrase, every action has an opposite and equal reaction, sometimes in the context of some very trippy stuff like, I don't know, New Age voodoo or something. But this actually makes a reference to the third law of Newton's law of motions, the law of action-reaction. We've seen in the last few lectures, in the first two of Newton's laws, that they're involved in solving problems for balanced forces and unbalanced forces. But now the third law, the one we're going to talk about today, is usually used conceptually within problems. So usually we don't have an explicit question that directly involves the third law. Okay, enough chit-chat. Let's look at the law. It states that every action has an equal reaction in the opposite direction. Sounds kind of abstract in a sense, right? Well, it simply means, in the physical sense, that if object A exerts a force on object B, object B will also exert a force on object A that is the same in magnitude but opposite in direction. And this statement covers it very comprehensively. We have the force exerted by object A on B being equal to the magnitude of the force exerted by B on A but opposite in direction. And these two forces are called action-reaction pairs. Now this might not seem very intuitive at all, because it means, say if you were pushing a dinosaur across the room in that direction, the dinosaur will be pushing back at you at the same magnitude of force. Given this picture that we have over here, a question that I had when I first learned this was, if, say, I was pushing a dinosaur, and a dinosaur was pushing back at me with the same magnitude of force in opposite direction, how can anything move at all? Wouldn't all forces balance out? That was my big question. Let me illustrate this concept with an example. Say we had a dinosaur standing on the floor. Over here's the floor, and it's standing there. Now we'll want to draw the free body diagram of this dinosaur, and we have, it's pretty easy, right? We have the weight, force of gravity, and we have the normal force. Now my question for you is, what is the action-reaction pair of the weight force? You probably say, man, you're insulting my intelligence. Of course, it's the normal force. But you'd be wrong. And the reason is that action-reaction forces must act on different objects. But the normal force and the weight force are both acting on the same object, our dinosaur. So they can't be action-reaction pairs, even though in this case they have the same magnitude and opposite directions. Now back to the question. So what is the reaction force to the weight force? Well, let me draw in the earth for you, because the dinosaur is standing on the floor, which is part of the earth. Sorry for my very crude drawing skills, but you get the idea. Remember how we talked about every object exerting a gravitational force on any other object, Newton's law of universal gravitation, although the amount is usually so small that we don't really care about it. In that light, the reaction force of the weight, which is the gravitational force exerted by the Earth on a dinosaur, is the gravitational force that the dinosaur exerts on the Earth. Sure, this is a very tiny amount, so we don't really feel the effect, but definitely, conceptually, it is there. And these two, the same colored ones, are action-reaction pairs, not gravity and normal force. Now similarly, the reaction pair to the normal force, which is the force exerted by the Earth's surface pushing up on a dinosaur, is the force exerted by the dinosaur's feet pushing down on the Earth, which is once again a very small force compared to the giant mass that is the Earth. Now let's bring it back to my original question, which is, how can anything move if all forces cancel it out by action-reaction? Which by now you probably realize it's probably a conceptually incorrect statement. But to show why it's incorrect, let's look at our rocket launch once again. Now don't try this at home. Yeah, I'm trying it at home. Hold it right there. In a rocket launch, we can tell that the force exerted on the rocket is, well, in this case, it's definitely towards the left because it's accelerating towards the left, right? Now, if a reaction force was also acting towards the right at the same time, and these two are have the same magnitude, then well, you wouldn't expect the rocket to move at all, right? But once again, we'll be thinking of action-reaction forces as acting on the same object, just like in the dinosaur. And we've already talked about how that is incorrect. So that's wrong. It turns out that the force that pushes the rocket leftward is the action-reaction pair of the force that pushes gas in the rightward direction. And that's why the rocket gets to move. These two are action-reaction pairs. This might be a little less obvious because, you don't really see the forces exerted on the gas, but you get the concept. By now, I hope you're very comfortable with this third law, at least conceptually. You get it, and the common misconceptions associated with it, because now we're going to use it on a problem involving balance forces. See you soon.